There's a hidden component behind your dashboard that's quietly breaking down, and you've probably never connected it to that function your car performs on its own every time you brake at a red light. It's called the starter motor, and for nearly 100 years it had one job so simple nobody paid it any attention. Turn the engine over 3 or 4 times a day, work hard for about 2 seconds, then rest for the remainder of the drive. That balance, which worked flawlessly for generations of cars, broke the day the industry decided to shut off and restart your engine automatically at every single red light. In this video, we'll show you why that decision, marketed as a harmless eco-friendly upgrade, might be setting you up for one of the most expensive repair bills of your car's entire life. To understand why start-stop puts so much pressure on this part, we first need to understand how a traditional starter motor actually works. It's essentially a high-torque electric motor connected to a mechanical engagement solenoid and a gear called the Bendix pinion. When you turn the key, or press the start button, the solenoid receives an electrical signal and does two things at once. It pushes the Bendix pinion forward so its teeth mesh with the toothed ring on the engine's flywheel. At that exact same instant, it closes the main electrical circuit connecting the battery to the internal windings of the starter motor. That closing triggers a massive electrical surge, sometimes hundreds of amps in a fraction of a second, all of it dedicated to overcoming the inertia of cold pistons, heavy rods, and thick oil film inside cylinders that haven't warmed up yet. As soon as the engine fires and starts spinning faster than the starter itself, a one-way clutch inside the Bendix disengages. This prevents the flywheel from spinning the starter motor at speeds that would destroy it, and the whole system goes back to rest. In a car without start-stop, this violent sequence happens only a handful of times a day, giving the system hours to cool down and recover between uses. But in a modern car equipped with automatic start-stop, that same electrical surge and mechanical impact repeats dozens of times during a single commute. Automakers are fully aware of this, which is why they redesigned the traditional starter into what the industry calls a heavy-duty or enhanced starter motor. They replaced classic copper graphite brushes with silver graphite and synthetic carbon composites, built to resist thermal oxidation and friction across thousands of hot cranking cycles. They reinforced the internal gears with hardened alloy steel, upgraded the coating on the Bendix pinion teeth, and swapped standard bushings for needle roller bearings capable of handling constant radial loads. These are real engineering upgrades. The problem is that no material upgrade can override the laws of physics, and that's where the real wear begins. The number one enemy of any electric motor under heavy, repeated load is heat. Every time the starter engages, current passing through its copper windings generates resistive heat, and that heat doesn't scale evenly with current, it scales much faster. In a traditional setup, the starter has hours to dissipate that heat into the engine bay before it's called on again. But in heavy city traffic, a start-stop system can trigger the starter every 20 to 30 seconds, giving it no real time to cool down. Over the years, that accumulated heat starts degrading the enamel insulation on the copper armature wires, creating microscopic cracks. Through those cracks, current begins leaking between neighboring coils, creating small internal short circuits. Those short circuits reduce the torque the motor can generate, so the system compensates by demanding even more current for the same crank. That's a feedback loop that accelerates its own destruction, working silently mile after mile until one day the car simply won't start. But heat is only half the problem. The other half is purely mechanical, and it comes from the physical impact the Bendix pinion takes every time it meets the flywheel's ring gear. To make start-stop feel instant to the driver, many automakers develop what's known as a change-of-mind starter. This system uses two separate solenoids. One controls the mechanical movement of the pinion, the other controls electrical power to the motor. This dual architecture lets the car's computer launch the starter pinion toward the flywheel even while the engine is still spinning down mid-shutdown. Picture this. You stop at a red light, the engine starts shutting off, but you change your mind and hit the gas before it fully stops. In that instant, the computer calculates the exact speed the flywheel is still spinning at and fires the pinion to try to mesh with it mid-motion. The result feels almost seamless to the driver, a restart delay of just 300 milliseconds. But the mechanical violence behind that software trick is very real. Even the most precise crankshaft position sensors can't perfectly synchronize pinion speed with flywheel speed in real-world driving conditions. So every single one of these restarts ends in a microscopic metal-on-metal impact. Over time, that repeated impact causes pitting, deformation, and wear along the edges of the teeth, both on the pinion and on the flywheel's expensive ring gear. When those teeth wear down or break off, the pinion can no longer mesh properly, and that's when you hear that horrible grinding sound announcing the car simply won't start. And that is not a minor repair. Replacing a worn starter is already an expensive job on a modern car. But replacing a damaged flywheel ring gear requires the mechanic to drop the entire transmission, a job that easily runs $2,000 to $3,000 in parts and labor. There's another factor almost nobody explains: the extra mechanical resistance from a warm engine. When the engine shuts off at a red light, it's still hot, with aluminum pistons, steel rings, and cylinder walls sitting at their tightest thermal expansion point, meaning maximum friction. On top of that, several cylinders are still sealed with a compressed air-fuel mixture trapped inside. So when you release the brake, the starter doesn't get the benefit of a gradual spin-up. It has to instantly overcome maximum friction and cylinder compression from a dead stop. That instant demand forces the starter to pull its absolute peak current, hitting the entire electrical system with a surge that a standard battery was never built to handle thousands of times a year. That's why almost no modern start-stop vehicle uses a traditional lead-acid battery. Instead, they rely on AGM batteries, absorbent glass mat technology, or enhanced flooded batteries, paired with a smart sensor mounted directly on the negative terminal. An AGM battery uses microscopic fiberglass mesh to hold the electrolyte, allowing it to tolerate much deeper charge cycles and recharge faster than a conventional battery. The catch is these batteries cost 2 to 3 times more than a standard one, and they have a surprisingly short lifespan under the relentless cycling a start-stop system demands. When the smart sensor detects the battery's charge dropping below a certain threshold from constant starter cycling, the car's computer simply disables start-stop to protect the electrical system. Here's the irony almost no driver knows about: the same system meant to save you fuel is the one wearing out an expensive battery ahead of schedule. That forces an early replacement that erases any real savings you made at the pump. And as that AGM battery ages and its internal resistance climbs, the starter receives lower voltage on each crank, so it compensates by demanding even more amperage for the same torque. That combination of low voltage and high current creates electrical arcing across the solenoid contacts and carbon brushes, accelerating their electrical wear too. Facing all of this, some manufacturers simply abandon the traditional starter motor altogether. Mild hybrids, for example, often use what's called an integrated starter generator, a brushless electric motor mounted directly between the engine block and the transmission. Because it's bolted straight to the crankshaft, this system eliminates the Bendix pinion, the flywheel ring gear, and all mechanical impact entirely, using electromagnetic induction to spin the engine up to idle silently in milliseconds. Other manufacturers use belt-driven starter generators, which do a similar job through a high-tension accessory belt, but neither of these solutions is free. Belt-driven systems place constant lateral load on the crankshaft pulley, the tensioners, and the belt itself, requiring specialized belts that are far more expensive to inspect and replace. And if an integrated starter generator fails in a mild hybrid, you're no longer talking about a $300 bolt-on part on the side of the engine. Because it's sandwiched directly between the engine and the transmission, repairing it means dropping the entire drivetrain with bills that can easily hit $4,000, $5,000, even $6,000. So what does all of this mean for the vast majority of ordinary cars on the road today, the ones still running a reinforced Bendix starter and not a hybrid system? It means start-stop is, in practice, a pure mechanical trade-off. In exchange, the driver gains a 2 to 5% improvement in city fuel economy, something like $50 to $100 a year in gas. Meanwhile, quietly in the background, it's accumulating thermal and mechanical damage on a starting assembly that isn't cheap to replace. Every red light, every drive-through line, every traffic jam forces the pinion to slam against the flywheel's ring gear and dumps hundreds of amps into windings that never really get to cool down. After 5 to 7 years of intense city driving, that constant cycling degrades the brushes, pits the solenoid contacts, fatigues the one-way clutch, and rounds off the precision teeth on the flywheel ring gear. Add in the near-inevitable cost of replacing an AGM battery every 3 years, plus the eventual starter or ring gear replacement, and the supposed savings from start-stop completely evaporate. Understanding the physics behind all of this, the heat building up winding after winding, the mechanical impact repeating thousands of times, lets you see past the eco-friendly marketing. Start-stop is in large part a system designed to meet government fleet emissions targets, at the expense of the owner's long-term mechanical reliability. That's why many technicians recommend something as simple as manually turning off start-stop with the dashboard button every time you start the car. That 2-second habit spares your starter motor, your flywheel ring gear, and your AGM battery from thousands of unnecessary stress cycles. It could be the difference between a starting system that lasts the life of your car and one that leaves you stranded ahead of schedule. It's worth being clear about something so this doesn't come across as a blanket accusation against the technology itself. Not every car wears out this way, and not every driver will notice it the same way. A car used mostly on the highway with few stops and restarts per trip barely puts any extra demand on the system at all. The real punishment shows up in heavy city driving, in cities with a light on every other block, in short 10 or 15-minute trips repeated several times a day. That's where the reinforced starter, the AGM battery, and the flywheel ring gear are pushed right up to the limit of what they were designed to handle. If your daily routine looks more like that, paying attention to the system stops being a curious technical detail and becomes a maintenance decision with a direct impact on your wallet. This isn't about demonizing a technology that, when properly understood, serves a real purpose in the auto industry's push to cut emissions. It's about understanding the hidden cost that rarely makes it into the sales brochure, so the decision to use it or turn it off is actually yours, and an informed one, not just a factory default you accept without ever asking what's really happening underneath. Next time your car shuts itself off at a red light, you'll know exactly what's going on beneath your dashboard. You'll know how much heat is building up in that copper winding and how many silent impacts that ring gear is absorbing, one that, sooner or later, is going to send you the bill.